Okay, so I'm going to be giving a talk on the tutorial on GANs. And probably most of you are exposed to GANs now, and some of you have used them. Some of you have papers on them. So GANs are a fairly recent method, and they've given some really good results. So they are a generative modeling technique, and as you can see, they can generate pretty realistic faces. They can be used for style transfer, super resolution, you name it. They've got pretty good results. Okay, but before I go on to GANs, let's close this and talk about generative modeling in general, right? Okay, so what do we call traditionally a generative model, right? So we'll call a generative model something that takes some assumptions, it builds a model, and then it has some data, and it fits that model to the data, right? Okay, in this particular talk, let's just consider a generative model anything that when trained on data coming from a distribution is able to produce samples that are likely to come from that distribution. Okay, clear so far? Cool. So let's see traditionally, how did we do the training of generative models? So we have something. So we have, let's say, a model, and that relies on certain parameters. Let's call them theta, and we would calculate these parameters using maximum likelihood estimation, right? So, and then that would be given by this, right? Right. This is just a data point. And this would be my maximum likelihood estimate, right? Oh, sorry, low likelihood. It would be a multiplication if there were independent, identically distributed samples, and then we just take the logarithm that turns it into a sum. That's how we get low likelihood. Right. So we want to maximize this. Right. Let's just take this to the limit. Let's take it to the limit where n equals infinity. And then this will turn into an integral, right? And that will become log theta xi times pd. This is our data distribution, right? Okay, cool. And we want to minimize this, right? Sorry, we want to maximize this. So that's equivalent to minimizing this. Okay, cool. And now, let's just, if we're minimizing this, when we're doing this with respect to the parameters theta, then we can still add something that's a constant with respect to theta, and that shouldn't change the minimization problem, right? Okay, so let's just add this. Right? That's what we've added. Nothing here depends on theta, so we can do that. Clear? Cool. So then what happens here is this ends up being sorry? Okay, this. Right?
Is the ratio is PD P theta or PG? What is PG?
Sorry, P theta, no, sorry. This is from later on when I go to, yeah, that's P theta, yeah. Sorry, PG is when I turn it into a generator, later on. So yeah, P theta, okay, this is our model distribution, okay? So this you'll identify as the Kullback-Leibler divergence, right? Of PD to P theta. Okay. So that's what we do when we maximize the likelihood, we minimize the Kullback-Leibler divergence. We just proved that. Okay, no questions, right? Okay, so let's see what this means, minimizing this. Right. So let's see when we have p theta, which is much smaller than p d, right? Let's take, for a certain space, this is going to be smaller than that. So what does that mean? That means our generating distribution, our model distribution, has a very low probability of generating this sample, right? But the actual data, but the actual distribution has a very high probability of generating it, right? This is a very likely data point from the real distribution, right?
Sorry, what was again the smaller sign? Like
this one is much smaller than this. So this one, let's say 0.
Would you like to define what the distribution much smaller than the other one means?
So let's say you have this is your PD, right? And this is your P theta. Sorry, this is your P theta here. Right? In this area, right?
Okay, fine.
This is much smaller than this. Okay? Cool. So if this is much smaller, what happens to the callback library divergence? Then if this is much smaller, then the KL will be very big. That means it has a high cost associated with this, right? So if we're minimizing it, this is going to be a very big penalty. So this is probably not going to happen, right? We're not going to. Basically, what we said now is we're not going to produce. We're going to associate a very high cost with not putting enough mass on the entire support of PD. Does that make sense? If not, I'll have an example afterwards, which will. Right, so let's take the opposite case, where PD is much smaller than P theta, right? And then in this case, KL will be very small. But what does this mean, right? If PD is very small, that means the actual probability of the distribution generating the sample is very small. But P theta is big here, so the probability of our model generating the sample is big. Right? So this is actually an unrealistic sample that we generate here. Because it has a very small probability that it will be coming from the distribution, the data distribution, but very high probability that we'll be generating it. So just to show you an example here, is if this was your PD, right? And this was your P theta. Sorry, let's make this multimodal. If this was your PD, and your P theta was like this, right? So we've seen it's matched this mode perfectly, but here, it's not matched it. So we fall into this category here, and this gets assigned a very high cost. So this gets penalized, so we won't ever have this. We're maximum likelihood. But this case, right? This one will get a very low cost, 0 cost here. If this matches perfectly, we don't care about this. So what's the problem with that? When we're here, we're generating completely unrealistic samples and assigning 0 penalty to these. So it's quite likely that we'll have unrealistic results. That's what it says. Maximum likelihood probably gets you unrealistic results. Right? So, okay, why do we do this? We did this to show that GANs don't do that. So now we can talk about GANs. Any questions so far? All right.
Excuse me, on my IT, apparently it's upon the projector.
No, that's all right. We've solved it.
Solved it?
Yeah.
Okay, thanks.
Okay, so now let's talk about GANs. So GAN is made up of basically 2 components, right? You've got a generator and a discriminator. And the generator, it's you can think of it as a function. What it aims to do is it aims to produce samples that are very likely to have come from the data distribution. That's what the generator does. The discriminator acts as a classifier. Its goal is to distinguish samples that are coming from the data distribution and those coming from the generator. So if I were to write these as functions, then G takes in an input Z, right? Z is samples from some prior PZ. And as output, so that's the input. And then as an output, it produces a sample X from PG. Right? This is just the same, this is the model distribution that we had before, right? The P theta. This the G takes the role of that. Okay, and the discriminator takes in as input NX, right? Which can be coming either from PG or PD, right? The data distribution that we had before. This is the generator distribution. That's what it takes in. And outputs a probability, so that's between 0 and 1. A probability that the sample we have belongs to either the data distribution or the generator distribution. 1, let's say, for when it belongs to the data distribution. So far clear? So if we were to look at that, give me 2 seconds. Yeah. So if we're to look at that, then this is the network that we've built, right? If you consider, so this is a function. Let's say it's a neural network because most of the times it is. Then we get something like this, right? We get a generator. It's given some input from some latent space. That's our z's. It produces some fake samples, and then those go to the discriminator along with some real samples, and then the discriminator guesses if this is a real or a fake sample, right? And then we train this. Let's say we train all of this based on the result of the discriminator, right? And we train it using backpropagation because we have neural networks. The idea is that when the generator and discriminator have converged, the generator has produced such good samples that it will fool the discriminator. And they're basically playing a game between the police and counterfeiters, is what Ian Goodfellow brought up as an example, right? So the generator is trying to be the best counterfeiter, produce the most realistic looking money, and the discriminator is playing the role of the police trying to identify. But at the same time is also giving hints to the counterfeiters by saying what went wrong, let's say. This is what happens through backpropagation. Okay, back to the board. Questions?
Just to clarify, the discriminator is the only one that takes in real samples? And
Yes.
Backpropagation, the generator gets feedback from...
Yeah, so yeah, all the backpropagation goes all the way through.
Yeah.
Right, this is an end-to-end thing. Okay. Right, that's done. Right, so now that we've defined these, let's go ahead and give a cost to each one. So the discriminator, we'll give it a loss which we'll call JD, right? And this is a loss that depends on the parameters of the discriminator and also the parameters of the generator, right? So basically, think of it this way. The ability for the discriminator to discriminate between real and fake samples also depends on the ability of the counterfeiter. If the counterfeiter produces very crappy looking samples, then the discriminator has a very easy job, right? But if it's very hard, then this will also affect the loss of the discriminator. Same goes for the generator actually, which will have a loss JG, and will also depend on both these parameters, right? Okay. And the discriminator is trying to minimize this. So this one is trying to minimize by according to the parameters theta d, right? And this one is going to get minimized with respect to theta g, right? Okay. So what we see here is the definition of a game, a two-player game, right? It's a case where I have a loss function, but it also depends on the parameters of another player, and I have no control over these parameters. So the same way that an optimization problem solution is a local minimum or local maximum, for a game, the solution is a Nash equilibrium. And what a Nash equilibrium really is you can think of it as a state in which no player has any incentive to change their policy. Right? It's a state where if you change your policy, you'd end up getting less reward. Does that make sense? Cool. Okay, so now we dive slightly deeper, and we'll have a look at this loss function here. So let's assign a loss function to this, right? And we do cross entropy loss function, right? So And is it okay if I delete that? If I right? Okay, just cross out. Yeah. Okay, so let's just write this out. One more, let's write this out, the expectation out. So we'll get over x log d of x dd. So this is over x, right? We're just doing the integral, and this is over z. And this one will be log 1. So far so good? This is just expanding on this, right? Now this one here.
There's probably a minus in the first.
Yeah, sorry. Minuses will go very easily because I tend to forget them, okay? Okay, so here, this one, we can write this like that. So PD and so dependent on x, and PZ is dependent on z. Right, so we can write this as that. This comes from something called the law of the unconscious statistician. It's just basically tells you that when you have an expectation of g of x, then that one is equal to either g and the distribution of g, or g of x and the distribution of x. In our case, z, let's say. The distribution is. Right, so we just replaced this with that. That's all we did here. Okay? Cool. So this one we just put this one down as is. Okie dokie. Alright. All right, we've done this. So let's see. So basically, this is our loss function equals this. Now, I can just put them all because they're both now with respect to x, the integrations. So we'll put log d of x, pd of x, plus log 1 minus d of x, pg of x, right? Okay. So this is one big integral. That's what the loss of the discriminator is. And we want to minimize that, right? So if we want to minimize this, we want to minimize what's inside it, right? And then one way, so if you think about this, we can write this in this form, right? We can write log b times a plus c log 1 minus b, right? So just b is down this, d. This is a, and then this is c. Right? This is all I've done is set these variables, and then this becomes that. Right? And we want to minimize the loss with respect to the discriminator to find what the optimal discriminator is going to look like. So, we basically do dj db, which is the same as doing with respect to the discriminator, and we'll come up with a solution which looks like b equals a over a plus c. Yes. Okay. Which means that the optimal discriminator. Alright, here. Yeah.
Could you please write somewhere like the function of pg with pz respect to pz or something? How do we written that before?
Which one?
P to g with respect to as a function of p to z.
This is a function.
P to g, like third line.
Yeah.
So
this is not we don't care about this, right? We don't know what the mapping from this to this is. This is what the cautious statistician tells you, is that you can, without knowing, basically it's usually used for the reverse, is without knowing what PG is, you can calculate this using knowing PZ, as long as you know that G is a function of Z.
Because you take the integral of it, right? So
Yeah, I'm not referring to that actually. I'm referring to the third line. The last is PG. Yeah. So you replace that with PZ above.
Yeah, I also replaced this with x.
Yeah. So that needs to be a function of. So to replace. So the integral on the second line was d zeta. In the third line is dx. Right, so you have to have a relationship of
Yeah, this was going to be like that. Yeah.
d zeta and then dx.
Yeah.
Yeah. So you have to have a relationship of x.
Well,
and
this
zeta.
is what tells us this.
Okay.
Well, in a way, it's because the discriminator doesn't actually have access to the theta g, only observes the probability outputted by g.
Yeah.
Okay.
Okay. So we were here, so we were going to write the optimal discriminator, which will end up being, based on that formula there, PD over PG plus BD. Right, this is the optimal discriminator. So far, this tells us nothing. Okay. But let's keep that result, and let's get rid of the rest. And let's have a look at, so we've seen what happens with the loss of the discriminator. We've assigned a cross-entropy loss for that. And now let's assign a loss to the generator, right? So with GANs, we play usually something called a zero-sum game. Which means that the loss of one player is going to be the gain of the other player. And vice versa, right? So every penalty you incur, the other player gets a reward for, and vice versa. So that means that GG, the loss of the generator, is going to be negative loss of the discriminator. Does that make sense? This, if you sum these up to zero-sum game. Okay, so. Right. Okay, so now let's take the loss of the generator and have a look at what the optimal generator will look like, right? But before we do that, let's talk a little bit about this game. So if once we've done this, we can then use this loss. We can just minimize with respect to one loss function, which will be this, and then we have what is called a min-max game, right? We want to minimize with respect to the parameters theta g, and then we maximize with respect to theta d, v, right? Is that clear? We're minimizing this before. We want to maximize this for the discriminator because it's got a minus, right? So that's the discriminator, and then the generator is just minimizing this, right? Everyone following? Yes? No?
So first of all, why? I know you mentioned that it can be a zero-sum.
It is a zero-sum game.
Why that?
We just defined it, so we want it to be a zero-sum game. Okay, so basically we want to solve this problem, right? Okay, so let's try to solve. So this one we already have a solution for, right? We just did it before. It's this. So let's see what the minimum of this will be, right? Let's just write it out. Again, we write the cross entropy. And I'm using the optimal discriminator because that's what we've received for maximizing this.
Just tell me, why do you change the notation? I mean, do you have a reason to use
V, you mean? No, we could use JG if you want. That's the notation that was in the paper, basically. Okay. I've tried to keep the notation as consistent. This is the only time I'll do this. Change. Okay, so we got that. Plus, remember we had a minus here and a minus here, but now because we've got minus j, these cancel each other out. And then we get log 1 minus d star of x. Right, this is p, this is overall x in pd, and this is overall pg. Okay? Okay. And we want to minimize this. This is what we want to minimize for the generator. So, if we want to minimize this, then we should be okay minimizing. Oh, sorry. Actually, we can. Before we do that, let's go ahead and replace the optimal discriminator with what we know from before, right? So then that will equal log PD over PG plus PD plus log PG over PD plus PG. Right? Just all I've done here is I've flipped these. If you do the calculations here, it just works out to be that, right? Okay. So if I'm minimizing this, I can minimize this plus some constant, right? No, hold on, right? Sorry. I can multiply and divide this by a constant. That's what I mean. Sorry. So if I did this, right? Divide and multiply this by 2. Nothing changes in this fraction, so I'm free to do that. So I'll do that, and then I'll take them out of the logarithm as well. So I divide and multiply each one of these by 2. So I get log, right? So that's 1. That's the division, and then the multiplication will look like this. Okay? See what I did there? So this one obviously is the same as multiplying it by 2. No magic so far. Then I do the same for this term here. Right? And then this one will end up being PD plus PG. Okay. So this is so far this is the loss function of the generator. If you take a look at these, right? This is the Jensen-Shannon divergence, right? It's 2 Jensen-Shannon divergences, but this is the definition of the Jensen-Shannon divergence, right? It's just 2 Kullback-Leibler divergences added together, right? And then some constant.
The last term is Z as well?
It's a 2.
It's a 2, sorry. Yeah.
Okay,
So yeah, just divide and multiply by 2, right? Sorry for this whole thing. So in the end, this will end up being two Jensen-Shannon divergence minus log 4. Okay? Right. So this is what the generator is minimizing, right? I'll just write just so we're clear. Right? This is the correct notation. Okay. So when is this minimized? We know that the Jensen-Shannon divergence will be the smallest point is 0, and that only happens when PG equals PD. Right? So for their optimal generator, and obviously this is a constant, so we don't need to care about it when minimizing, right? So we know that for the optimal generator, what we'll get is this. Okay, and even though this was not a very significant result in terms of what it was telling us, this is a great result. Because it basically tells us that when we have an optimal discriminator, and we optimize the generator, then PG will exactly match PD, which is great. Okay? So, oops, sorry. So what will happen in this case? Let's assume the generator has also now converged to the optimal generator. Then the discriminator will end up being this 1/2, right? Because PG equals PD, right? So this will end up being 1/2. What does that mean? That means that the generator has gotten so good that basically the best discriminator is going to be a coin toss, right? It has no way of knowing. That's our hope with GANs. Okay, this should open, so I can show you some examples. Yeah. Right. Cool, I'm okay to remove these erases. Yeah.
Sorry. You mentioned that that is the best generator you can get is the PG equals to PT, which means that the best generator means it generates something exactly as data.
Yeah.
So in that case, the discriminator is like you saw a coin.
Yes.
And you get like 0.5
Yeah.
probabilistic, which means I guess that's the reason why we have zero-sum game, because zero-sum game means if one side played too well, another side played bad.
Yeah.
So if this generator played too well, the discriminator played very bad.
Correct, yes. So basically, yes, okay, I see where you're getting with this. So if the discriminator is doing a coin toss, that means not only the discriminator is half times wrong, but also it's half times right, so the generator is only fooling it half the time.
Yeah, so in the other way, if the discriminator is too good, the generator will be bad.
Yes, yes.
So they are
Yeah, because everything is judged based on the performance of the discriminator, right?
So in this case, if it's a zero-sum game, how could you optimize this? Because if you optimize one part, you actually undermine another
yes,
part.
you reach the equilibrium. You reach the point in which there's not one player. Let's say no player has an incentive to change their strategy. Let's say the way they're producing samples in this case, and the way they're discriminating samples.
Mm-hmm. Why they cannot change the strategy?
Because if they were to change it, they would lose out. So if the discriminator is not doing a coin toss, but the samples are so perfect that you can't discriminate, then it will actually end up getting a worse result, right? If you have no idea which one's better, then your best guess is a coin toss. It's not something else. Does that make sense?
It's like dividing a cake. If both people are as strong as each other, they'll divide it in two. Otherwise, the other one's gonna get more upset.
Yeah.
Concretely, also, if one of them gets better, then he will get more information from the gradients, and so he will get better.
Oh, yes.
Okay, cool. That goes away so that you can see this pretty picture. Okay, and this is what we were talking about, right? So in the beginning, you have two distributions, the black one and the green one. The green one is what the generator produces, I think, and then the black dotted one is what the actual distribution is, and then this is, just think of it as a decision boundary between these two. So at this point, we've not trained our generator, so here we actually train it, and it becomes PD over PG plus PD. Right? So then this is our decision boundary, and slowly the generator will learn and slowly move this way, and eventually we get this, which is the discriminator is deciding based on the coin toss. This is 0.5, and then these have perfectly matched each other. Right? This image that you see in all the GAN papers is just telling you what we just proved right now. Cool? Okay. The next part is going to be painful. For me, not for you guys so much. Right. That comes off again. Oh, actually, could stay on for one more slide. Yep, it can. Okay, so one problem that we have with this is when we have this. When we take a step in a gradient descent step in solving this problem for the generator, right? This is just the part that depends on the generator, right? Then what we tend to have is when the discriminator is very, very confident, we tend to have vanishing gradients for the generator.
We tend to have?
Vanishing gradients for the gradient descent. One way to think about this is if they were completely disjoint and you were to plot the loss function, then you get something like this, where this is your discriminator confidence, and this is your generator confidence. You can see up here, like toward this side, the gradient, the slope of this is much less steep. Yeah? No?
No, but this makes sense. This is exactly why you have, because you're tending to go to this half. This is why it's happening. So the
Yeah,
gradient has to
but
be
it's
really-
so okay. If you have a very good discriminator, and there's vanishing gradients for the discriminator's parameters, that's fine because you're already approaching your optimum. But if you have a very good discriminator and your generator hasn't yet reached its optimum, actually that's pretty bad because it will slowly converge to that optimum. So for the discriminator it doesn't care, but the generator cares. Okay. Greg?
Greg,
Yeah.
is it clear? Okay.
Sorry. Forget that slide. That's later. Alright, so. Right. Okay, to deal with this vanishing gradients problem, a lot of people, instead of taking a gradient in this direction, they take a gradient here. They take this, the gradient of this problem, right? Which doesn't suffer from vanishing gradients. But so up until that point where we proved that PG equals PD, that was basically the GAN paper. So it came up with that conclusion, and then it's like, okay, that's fine. And then people started training GANs and found that there's actually some problems with them. There's mode collapse. There's the cases where you don't actually, which basically was this example we saw here, where we had two lumps here and there was only one there, right? So there was mode collapse, and actually the initial paper didn't really address these issues.
Didn't you say earlier that GANs did not have this issue?
That was maximum likelihood. You remember? No.
Yeah.
No, we were talking about GANs. No, the GANs, I said, yeah, in theory they don't have this problem, PG equals PD, but we'll see what happens in practice.
Okay.
And I didn't prove anything for the GANs yet. I just said that if everything works great,
Shouldn't have this problem.
it should actually match it perfectly, right? But let's see what happens in reality, because in theory we're also minimizing this. We're also taking a step in this direction, but actually more because of the vanishing gradients, we're usually taking a step in this direction, right? So let's see what happens in this. This one's going to be painful proof. Okay, so let's assume we have parameters of the generator theta, and there's a specific set of parameters theta 0 for which the discriminator is optimal, right? So we have an optimal discriminator. What that means is that according to the what we found before, we'll have PD over PG theta 0 plus PD, right? And then if we rearrange this, we can basically come up with a ratio of PG theta 0, oh, sorry, PD over PG theta 0 equals D star over 1 minus D star. Okay? All I did was rearrange. Cool? Okay. Now, let's go and, for no reason that's apparent right now, calculate the Kullback-Leibler divergence of PG given P D. Right? Okay. That one becomes log P G theta. All right, let's do that. And over PD. Right? This is just the Kullback-Leibler divergence formula, right? Okay. And we can do the same trick we were doing before, which is multiply and divide by a number, right? And in this case, we'll just do, we'll multiply and divide with PG theta 0. So that will end up being PG PG theta over PG theta 0. And plus PG theta 0 over PD, sorry, log. That's not gonna fit. And how will I fit this? I'll just do it like that. PG theta 0 over PD. Okay, took us a while, but we got there. So this thing here. Okay. Da-da-da.
Wait, what is theta 0?
Theta 0 is the parameter set. So it is the parameter set for which we have the optimum discriminator. So at that time we have an optimum discriminator. Okay, and this is just the distribution we get from the generator when we have that set of parameters. Okay. Right. So 1 second.
So
Right.
why does that collapse to 0? Because that's actually what you claim.
No, I didn't. All I claimed was that I can multiply and divide this by that number. And I can.
Wait, by which number?
By PG theta 0. See, it appears here and it also appears here.
Ah, I see.
Right.
Okay.
So that's all I did there. Okay. So if we have a look at, for a start, let's have a look at what this one is. So that is the Kullback-Leibler PG theta, PG theta given PG theta 0, right? This is just the formula for this. And then this one here, we can actually substitute in this, right? This ratio, because we know it. So it ends up being, did I write this the wrong way around? Okay, well. Plus log. Okay, so this is just from substituting this in. Okay? And, oh, sorry, expected value. Okay, and if we were to take the gradient of this, right, then we'd have to take the gradient of that. So let's take the gradient at theta equals theta 0. Right, so KL PG theta equals theta 0. That will, so this one, at theta equals theta 0, these two will match, so that's 0. That makes sense? And then that's just the gradient of this. Yeah? So far, so good?